Hello, my name is Victor Chavalti and today I'm going to be talking about the work realized by my group, consisting of me, Antônio Rensi, Denilson Barbosa and Gerda Cristal Silva. The work's title Prediction of Differentially Expressed Genes and Subtypes in Breast Cancer using K-nearest Neighbours, Support Vector Machines and Random Forest Methods. This is the outline of today's presentation, so let's begin. Breast cancer is one of the leading causes of death in women in most developed and developing countries. In the US, falling second only to lung cancer. In 2020, there were 2.3 million women diagnosed with a subtype of breast cancer and 685,000 deaths globally. At the end of the same year, there were 7.8 million women alive diagnosed with a subtype of the disease, making the world's most prevalent cancer. Breast cancer can be classified by its histological and molecular signature. This molecular signature gives rise to 5 subtypes of breast cancer: luminal A, luminal B, HR2+, basal-like, and normal-like. These histological markers, along with immunohistochemical characteristics and clinical pathological variables like tumor size and grade, are the most often used criteria in diagnosing subtype. However, there has been a surge of interest in the use of gene classifiers to perform this task. He et al. Managed to find a signature containing 206 genes which could be effectively used to perform molecular classification of breast cancer samples, and Parker et al. Managed to lower this bound by finding a set of 50 genes called PAM50, which is the new gold standard in clinical settings. Nevertheless, there is an inherent difficulty in performing gene classification with machine learning methods due to the large dimensionality of the data. There are 3 common approaches to this task: K-nearest Neighbours, support vector machines, and random forests. Each of these techniques approach the problem with a distinct methodologies and so distinct strengths and weaknesses. Our objective is to perform an analysis of efficacy of each of these methods applied to the classification of breast cancer molecular subtypes using a TCGA-BRCA cohort with over 1,000 samples. Data is publicly available via the CDC National Cancer Institute Data Repository and consists of over 1,000 samples of the gene expression of differently diagnosed breast cancer patients. Out of the 1,021 samples, 524 samples consist of patients with luminal I breast cancer subtype, 255 consist of patients of HR2+ breast cancer subtype, 178 of patients with luminal B breast cancer subtype, 79 consist of patients with normal-like breast cancer subtype, and finally 35 consist of patients with basal-like breast cancer subtype. As can be seen in these graphs, 86.1% of these patients are currently alive and 98.9% of them are women. In order to compare the efficacy of the distinct methods, we have implemented the following pipeline. The pre-processing stage will consist of downloading the data via the GDC repository using the R package TCGA biolinks. We generate the expression matrix and remove possible outliers. The data is normalized and enrichment analysis performed. We then reduce the amount of variables by manually selecting only those found by Hugh et al. And Parker et al. Unfortunately, the classification subtypes are badly misdistributed, with luminal A consisting of almost 50% of the population size. In order to correct for this, we artificially generate samples via the mode technique. We then perform K-cross validation for each technique, setting aside a testing set of 20% of the total samples. With regards to support vector machines, we vary the regularization parameter and the kernel coefficient under the Minkowski metric using radial basis function kernel in order to find the most efficient parameter. With the K-nearest neighbor method, we vary the existence of way by distance, where points further away have less impact in the classifications, which algorithm to use in order to perform classification, the metric, varying between the Euclidean distance, Minkowski's distance, and the Manhattan distance, and of course the amount of neighbors to be used. With the random forest method, we vary the amount of trees, the criteria to measure quality of a split, and the amount of features to consider when determining this best split. All these methods have been implemented by using the scikit-learn library for Python 3. To evaluate performance, we calculate the proportion of correct classifications performed in the testing set. Our results are as follows. After performing clearing and preprocessing, we obtain a data matrix of shape 1023 by 317. We equalize the distribution of classified as mode with a result of 524 samples for each classification. We then perform the cross-validation training, obtaining the following results. We can see that support vector machines perform the best with an accuracy of 0.92, and that the K-nearest Neighbours and random forest tied to second place with an accuracy of 0.85. The table shows the recall as well as the F1 score obtained by each method. We can also look at the confusion matrix for each method and see that luminal type A was the main source of confusion independent of the technique being used. Nevertheless, we can see that our methods perform exceedingly well. It would be interesting to perform the same analysis on other types of gene expression data to see if the results match. We believe that our results show that machine learning methods have useful applications in the clinical setting. Thank you very much.